Okay, so this is the second part of section 2.9, linear approximations. And first, I'm just going to show you kind of the idea behind them. This is what we would have done in class. So it says, draw the line tangent to this function at x equals -1. So if you have your straight edge, go to x equaling -1 and see if you can draw a tangent line there. Take a moment and see if you can do that. Mine will not be great, because I am on a tablet looking at a screen, but I'm going to try to do the best I can. And, you know, it is what it is. So we have our tangent line here. So that's A. And then this is a kind of a subjective question for B, but it says, at what values of x do you think the tangent line stops being close to this function? Estimate to 1 decimal place. So when you look at your tangent line, the question is kind of like, when does the line stop being near the function? Like, at what value does that happen? So for different people, depending on your tangent line, it might be different things, but I might say, like, I'm getting kind of far away over here. That difference there is kind of big. Over on the other side, yeah, maybe like here, it's getting to be quite a bit different than the line. Again, it's subjective because it's the value of being close. But I might say, for my picture here, -1.6, and on the other side, -0.3, something like that. Again, you might have slightly different values just depending on your tangent line, even though, I mean, there really is only one tangent line, but we're all drawing slightly different versions depending on what we have. So then the question is, what is the approximate value of the function at x equals -1.5 using the graph? What about the value at x equals -1.5 using the tangent line? So, you know, the idea here is at -1.5, you know, you're looking at these two values and you're noticing the y value for your line and the y value for your graph are actually very, very close together. So, you know, the idea there is just to recognize that both of those values are fairly close. So for the line's a little bit higher, so maybe I'll say -0.3 is the y value. For the graph, it's a little bit lower. You know, these are just estimates here, -0.4. But my point is just those two values are very close. And that's the whole idea behind linear approximations, is that by finding what is the tangent line to the graph of a function, you can actually approximate y values on the function based on the line, because near to wherever the tangent line you know, hits, the y values are very, very similar. So let's take a look at this function here. We have a point a, f of a, so down here is a. Now the line here, that's the line tangent to the function at a, and the function is just y equals f of x. So if I asked you to find the equation of the line that is tangent, so if I asked you to find L of x, and I said use these 2 points, you would want to understand that back, you know, from way back, we have that y minus y1 equals the slope x minus x1. And then we would just use the values that were being given. We are talking about at the value x equals a. So this is our point right here, a, f of a, that's x1, y1. And then our x, f of x is essentially our xy here. They're just the general other values, you know, on the function. And our derivative, or our slope, would be the derivative of the function at a. So if you can kind of take that all together, if you want, you can pause it and take a moment and see if you can write them down. So we have something that looks like this. And so again, this would be the equation of this would be L of x. And if I solve it for f of x, notice that I get f of a plus f prime of a times x minus a. Now the point of doing that and understanding that that would be the equation of the line tangent to the function is that f of x is approximately that y value of L of x. So notice you have this, between any 2 points, you have some difference in the y values. But very close to A, that difference is very small. Farther away from A, that difference is very big. So the y values, the L of x is the same as f of x for very close values of to A. So notice we have a little kind of a definition here. Basically what I was saying, for x values close to A, the function and the tangent line have very similar y values. Thus, linearization is a method of finding approximate values of functions. So the linearization, which is L of x, is just equal to that thing that we just found. So basically what it's saying is you can find y values just by using your function and its derivative and some value of A to find values very close to A. So let's take a look and see what we can do. So find the linear approximation to f of x equals x to the 6th at a equals 1. Use it to approximate the value of 1.02 to the 6th. So of course, you have every right to, the last thing we're going to do here is compare it. So this idea here is just us putting this in to see how close our approximation is. So I don't need to do it first, but I'm just telling you we can find this out by putting it into our calculator. I'm not going to tell you you're not going to be able to do that. But if you do that, you get this. What we're saying is with the linearization, we should get a number very close to this. And if you want to, talk to me about why would we use that when we have the derivative, well, we don't always, or why we can just plug it in. There are reasons, there are applications and stuff. Higher level stuff. So find f prime of x and f prime of a. So the things in order to do this, and you can just go back to the last slide if you want, and obviously just right above on your page and think of all the different things that we need. We need to find the derivative of the function, which we know. We need to find the derivative of the function at a, which in this case is 1. We also need to find f of a, which is just f of 1. Okay. And that tells us that we have our point 1, 1, because a is 1, and f of a, or f of 1 is 1. And then we also have our derivative at 1, which is 6. So we really have everything we need at this point to create the linearization. So we have L of x, so I'm just using what you have in the box from above. F of a is 1, and then f prime of a is 6, x minus, and then a, which is 1. So this is the linearization. So this is the line, the tangent line, to f of x equals x to the 6th at a equals 1. And then if you think about this, if you were to plug in 1.02, the idea here is that because that line is close to the function x to the 6th at a equals 1, the y value should be very close to 1. So because we're only 2/100ths away here at 1.02, we get 1 plus 6 times 0.02, and that's going to give us 1 plus 0.12, so we get 1.12. And then, of course, the big thing to see is that this is close to the actual value of 1.02 to the 6th. And so that's kind of the big idea with linearization. You find the tangent line, that's a linearization, and for any value that's close, you can do some approximations. So now we have another example. Linear approximation to the function, the cube root of x at a equals 8, and we're going to use it to do two approximations you can probably already guess if I were to ask you which one of these is going to give a closer, more accurate approximation. Hopefully you can think about that and tell me that answer pretty quickly. Let's see what happens. So we need the derivative of x. So we have x to the 1/3. So this is just our power rule. 1/3 x to the negative 2/3. There you go. And we're going to need to know that value at 8. We have 1/3, 8 to the 2/3. So 8 to the 2/3 is the same as the cube root of 8 squared, or you could also do the cube root of 8 squared, or you could do the cube root of 8 squared. Either way, the point is you're going to get 4. It's the point. And this is going to give you 1/12. So we need that value. And then we also need, f of 8. So f of 8. Put that in. So that's just going to go back into our original, the cube root of 8. You can tell me that is 2. Okay. So we have the point 8, 2, and then we have the slope of the tangent line at a equals 8. So now we're ready for our linearization. That's all that it is. So it's going to be the y value, 2, plus the slope, x minus 8. So L of x is approximately f of x for values close to a equals 8. So now if we plug those in, if we do L of 8.05, we're going to get 2 plus 1/12, and then 8.05 minus 8. And we can put that into our calculator, and that's going to give us about 2.00417. Now, the idea here is to see that that should be very similar to f of 8.05. And if you put that into your function, you're going to get about 2.00415,802. And you can check, make sure you can get that. So you're noticing that this answer is pretty exact. It looks like it's not until the 5th decimal place that you'd have a different value, and that would be just by 1. So it's quite a close approximation. And you can think about the way that curves work as well, and some curves obviously have steeper slopes and things, and so those would create larger differences in the y values quickly. Now if we do 25, you're probably not going to be surprised to find out, hopefully you already kind of picked up on this, but if we put in 25 and we do that work, we would get 3.4167. So we'd say, oh, well, the cube root of 25 is about 3.4167. However, if you were to actually put this value into your function, which is the cube root of x, you'd get 2.92 and then 4.01744. Point being there is, take a look at the bottom here, check the answers. Ooh, sorry about that. Check the exact answers. What happens to the approximation as the x value moves away from the value of a? So notice when we put in something very close to a, we get answers that are very close for the approximation or the function value. But when we put in something far, this is quite far away from 8, we see that our approximation, while not like crazy different, it's not like we got 3.4 and then like, 17, but it's still not a very good approximation because the tangent line is going away from the curve at that point. So we'll say y value gets further away. So the approximation isn't as good. So we're really only using it near where a is. Okay, a couple more examples. Find the linear approximation to f of x equals the square root of 2 minus x at a equals 0 and use it to approximate 1.9. So if you want in this case, the square root of 1.9, so if you want in this case, you could find the press pause, find the linear approximation, and then come back and check your answer. All right, so I'm going to have 2 minus x to the 1/2. I'm going to take my derivative, 1/2, 2 minus x to the -1/2. I'm going to plug in 0. That's always a nice value for a. Why not? Derivative at 0. It looks like I'm going to have 1/2 times, it looks like I'm going to have the square root of 2. So, oh, and I should have a -1 here. So I'm going to have, good, that's a chain roll situation there. And so I'm going to have 1 over root 2, and I'll put my negative right there. So the derivative at 0 is -1 over 2 root 2. Okay, so we have a negative value there. And then we also need f of 0. Plug that right back in, and you're going to see that we get the square root of 2. So we're ready for the linearization now, and that is L of x equals the y value, root 2, plus the slope. Slope's negative, so I'll write a minus, but you could do plus negative, that's fine. And then x minus 0, since that's the y value. And that's going to give us the square root of 2 minus 1 over 2 root 2 times x. So we don't have another value there, so that's kind of nice. And then our job is to use it to approximate the square root of 1.9. Now here is the slight difference between what we just saw and what we're seeing now. But we need to think about what we want to put in to this linear approximation. Because this linear approximation, you can see that when a is 0, f of x is the square root of 2. So we want to choose a value of x that's going to create the square root of 1.9. And that means choosing x to be 0.1. So notice the slight difference there because of how things are written. And so we're going to be plugging in 0.1 here. And that's going to give us the square root of 2 minus 1 over 2 root 2 times 0.1. Now this should kind of make sense because if you think about it, the y value at 0 is the square root of 2. So the value at, for, the square root of 1.9 should not be very, very different than the square root of 2. And so we're only just subtracting this little bit right here that comes when we multiply that out. So that's going to give us 1.37886. And the exact value, if you put the square root of 1.9 into your calculator, is 1.37840. So you can see it's a pretty close approximation to the square root of 1.9. I mean, to 3 decimal places, it's just a little bit off. To 4 decimal places, it's a little bit more off. But it's still close. I mean, that's the idea here. It's still close. That's the whole point. All right, let's do the last one. Use a linear approximation or differentials to estimate the cube root of 28, rounding to 5 decimal places. Hint, you'll need to first choose a function, then a good value for a. So it would be a great idea if you could pause this and see what you can do with it, but if you want to follow along, I'll talk about it now. For the video quiz questions, I'll mention that every morning I have eggs and sweet potatoes for breakfast, and that will be one of the questions to make sure you've been following along. So a little bit about me and my breakfast. Okay, so the idea is we need to choose a good function, and we're actually going to use a function we've already seen, the cube root of x. But the idea here is we have to choose the a, and you want to think about, is there a value for the cube root of something that would actually be kind of a reasonable value to basically, if you had the cube root of x, what x would you want so that you could create a pretty good tangent line there so that you could then estimate the cube root of 28. So if you're aware of your cube roots, the best A would be 27, so that based on the function that we chose, we would get that the y value there is 3. So that gives us our point, 27, 3. And then we still need our derivative. We actually already took it in an earlier problem, so 1/3 x to the negative 2/3. And then if we put in our 27, because we're trying to put in f of a, for f prime of a, and we're going to get 1/3 and then 27 to the 2/3. So hopefully with your algebra skills, you can do this, without needing a calculator, because you can take the cube root of 27 and then square it. And that's going to be 3 squared, or 9, which gives you 1/27. Okay, so now we have that L of x is 3 plus 1/27 x minus 27. And then because this is just the square root of x, and our a was 27, so we dealt with the square root of 27, the square root of 28 just involves plugging right in 28. So notice the difference between this and the last one. So 3 plus 1/27, and then 28 minus 27. That's really nice because that's just 1. So then you have 28 is just 3 and 1/27, because you get 1 there. And then you can do that in your calculator to get like a decimal so that we can kind of compare them. So 1/27, and then add that to 3. And I have 3.037037. Looks like that continues. And if we were to think about the exact, that's going to be the cube root of 28. So if we do the cube root of 28, so 28 I'm going to do to the 1/3. A little easier, I like it. And that's going to give us 3.036588972. We don't need all those decimal places, I'm just trying to show you. So in this case, if you were to round it to 3 decimal places, you'd be right. Any more than that, you're going to be a little bit off. But obviously, these are close values. So that's the big idea behind linear approximation. And from the first part, differentials, and that's the end of chapter 2. So after this, we head to chapter 3.